When we look at textbooks in econometrics or in statistics more generally, including machine learning, a lot of the books will make a lot of use of matrix algebra. So generally, we can describe models in two different ways. We can look at, we can provide a mathematical equation for one specific observation. So we can say for one observation at a time, this is how x and y are related to each other. Or we can look at an equation for an entire set of data at once. And in that case, we use matrix algebra. In this video, I want to give a very brief overview of the main operations in matrix algebra. And the main purpose is that you will be able to read the papers, that it doesn't look too cryptic. So let me turn to the slides. Matrix algebra has two main elements, vectors and matrices. We'll discuss vectors first. So here are some examples of vectors. Vectors are basically sets of numbers that have a fixed position. So if v is 3, 4, 1, and 5, then the first number is 3, the second number is 4, etc. It's not a set, not a collection. We cannot change the order and have the same vector. And a vector can have 2 items, 5 items, hundreds of items, thousands of items. It is just a series of numbers. In fact, one way of looking at them is actually as coordinates in a system. You can imagine you have one axis and another axis. Let's call this one x1, and we call this x2. We could have a point here. Let's say maybe this is at 5.4. Yeah. So this is at the 5,4 point. It's very difficult to write with this mouse. Yeah, so another way of writing that will be a vector. That is x equals 5 and 4. Yeah. So one way of thinking about a vector with 2 elements is that it is a position in a 2-dimensional space. Yeah? And so we can think of this as a particular position in a 4-dimensional space. So we can have a space with 4 axes, v1, v2, v3, v4, and then these are the coordinates. On the first axis, it's at position 3, on the second axis on position 4, and so forth. Yeah, so a vector is a set of numbers. So I should not use the word set because that is confusing. It's a series of numbers in a particular order because they are coordinates in a space. And so of course it's a different point. If I here go to 4.5, yeah, I'm at a different position. Yeah, so the vector 4, 5. Sorry for the writing. That's a 5. The point 4, 5 is in a different position in that space, and so this is very much a different vector. Yeah? So that's not the same as x. So a vector is a set of numbers that can also be interpreted as a position in a higher dimensional space. W is the same, so these numbers can be rounded numbers, they can also be decimal points. And sometimes we speak just in abstract terms. So for example, this beta vector, it has 5 elements, beta 1, beta 2, beta 3, beta 4, beta 5. So it is a point in a 5-dimensional space. But here I have left open where exactly this point is. Now you will see that V and W are written in a different way. And they are also then represent something differently. So V and beta are column vectors. W is a row vector. Yeah. When we don't specify throughout the slides, but also in most textbooks, if you see a vector described and they do not explicitly state that it is a row vector, you can pretty much assume it's a column vector. That is really the norm. The first matrix operation I want to discuss is the transpose. So vectors can be transposed, and that means turning a column vector into a row vector or turning a row vector into a column vector. And in both cases, the order of the number stays the same. So if the first number in the column vector is a 3, the first number in the transpose is also a 3. And we often denote this transpose with this comma. That's what I do throughout the slides. It's also quite common to do it with a capital T. So that is also a common way of phrasing the same thing in many textbooks. Either way, it means the transpose. So sometimes it's with this apostrophe, sometimes with a T, and it means the transpose. And so the transpose of the transpose is the original matrix back. Yeah? So if I transpose this matrix here, then this becomes a column vector with the first element 3, the second element 4, the third element 1, and the fourth element 5. And so we are back to the column vector on the left. Yeah? The next operation is not really a vector operation. It's more general math notation, but you will see it in a lot of different slides. So it's very important that you're familiar with this notation. So when I have a vector with these elements, I can also describe the different numbers with a subscript. I can say V1, and that is here is 3, or I can talk of V3, and V3 here is 9. Yeah? Oh. So V1 is 3, V3 is 9, and so forth. So we can talk about these numbers with the subscript. And what you will see quite often is that we will do that in slightly more generic terms by using a subscript such as I. So if I say Vi, I just mean the ith element in this vector V. And I can be 1, 2, 3, 4, or 5. Yeah? So it leaves it a bit more general. So here we see that we talk about the ith element in the vector V. And then this symbol here, this is the summation symbol. Yeah? So this is the Greek letter sigma, capital, stands for summation. And we usually say that here we give an indicator of the symbol that we use for counting. And this is how many we count. So this is a vector where we say n equals 5. Yeah, there are 5 numbers in this vector. Yeah, so that's in this case the length of the vector. So we will sum, whereby E captures the indicator where we are, 1, and then 2, and then 3, 4, and 5, and n is the maximum number that we count to. And we are going to look at this vector V and the ith element. So if I say the sum E of n V I, I'm really saying it is exactly the same thing as saying V1 plus V2 plus V3 plus, and all the way up to plus Vn. Yeah, that's what this is exactly what this means literally. Yeah, without having to know what V means or etc. If you see this, you can. If you see this thing on the left, you can think this thing on the right. That's what it means. And so in this case, V1 is 3, and V2 is 5, and V3 is 9. So we get the sum 3 plus 5 plus 9 plus 1 plus 3 is 21. Yeah? So this simply means taking the sum of a vector. So we can sum the elements of a vector. We can also use addition with vectors themselves. So when two vectors are of the exact same size, and they are either both row columns or column vectors or row vectors, so they have to have the same shape exactly, then we can add them together. And when we add them, we simply add the numbers for each row, for each element together. So for example, 2 plus 6 is 8, yeah? And 1 plus 9 is 10. And you can see that you can only do this if the vectors look exactly the same. So if the vectors have, if one has an element more than the other, then addition is simply impossible. So if you see two vectors being added, you can, in the text, you can assume that they have the exact same size, the same length. And we can do the same with row vectors, exactly identical. We can also multiply vectors with scalars. A scalar is just a number, not a vector or matrix. So you have normally never thought about scalars because you always think in terms of numbers when you think about math. But now we have vectors and matrices as well. So now we need to distinguish them. And if we just have a number that is not a vector or matrix, then we call it a scalar. And so when we have a matrix of a vector V with these 4 elements, 2, 3, 1, and 6, and we multiply this vector with a number, for example, 3, then every element is multiplied by that number. So 3 times 2 is 6, 3 times 3 is 9, 3 times 1 is 3, 3 times 6 is 18. Yeah, so multiplying a vector with a scalar, with a number, means that you multiply every element in the vector with that number, and you obtain a vector that has exactly the same shape, the same size, the same direction as the original vector. Okay, so far the operations have been relatively simple. We have vectors that are row or column vectors. We can take the sum of a vector, we can add or subtract two vectors. Subtraction is the same as addition, just the other way around. We can multiply with a scalar. Now we're going to do something that is slightly more complicated. We're going to look at the product of two vectors. Now for that, the rules are a little bit different. So we can talk about the inner product, and the inner product means that we turn one vector into a row vector and then multiply it with a column vector. Yeah. So first, V transposed is a row vector 5 times 3, 5, 3, 1, and 3. And we multiply that with a column vector 7, 6, 8, and 1. Yeah. And the result is just one number where we multiply this one with this one, and we add this times this, and we add this times this. Yeah. So you get 5 times 7, and you add 3 times 6, and you add 1 times 8, and you add 3 times 1, and the total sum will be 64. Yeah. So if we have a vector and we take the transpose so that we have a row vector, and we multiply it with a column vector, it is the sum of the product of all these elements. And to make this sum, of course, these vectors need to have exactly the same length. So we cannot calculate the inner product of a vector with 5 elements and a vector with 4 elements. Yeah, they have to have the same number of elements to make this operation possible. Notice that we can also multiply with oneself, of course. So we can do something like this. That means transpose the vector V and then multiply it with the column vector V. So then we get 5 times 5 is 25. 3 times 3 is 9. 1 times 1 and 3 times 3 is 9. So we get, what is it? 44, I think. Yeah? Yeah? So this is basically the same thing as saying this. We can take the sum, count up to n of Vi squared. Yeah? So this is the matrix notation of saying take the sum of squares of a vector. Yeah? Because this is 5 squared, and this is 3 squared, and this is 1 squared, and this is 3 squared. So if we do the transpose of V times V, we get the sum of squares of a vector. And if we didn't use matrix algebra, but we used algebra where we write for each observation, we would end up with this second equation. So that is the same. That is also 44. That's the same thing. Yeah? So the inner product is a row vector multiplied by a column vector that each have to have the same length. And the result is each element, the first elements multiplied, plus the second elements multiplied, plus the third elements multiplied, etc. And when you do this, the transpose of a vector multiplied with itself, you end up with the sum of squares. And that we will see quite often in econometrics. We are often thinking about sums of squares. So that equation you will see a lot throughout. Now, the outer product is a good bit more work to write down. So here, instead of having V transpose times W, so a row vector times a column vector, we have V times the transpose of W, which means we multiply a column vector with a row vector. Yeah? So V W is equal to a column vector 5, 3, 1, 3 times a row vector 7, 6, 8, 1. Yeah? And in this case, we get a large matrix that is 4 by 4, where the first number is the 5 multiplied by the 7, ends up is 35. And the second number is the 5 multiplied by 6, which leads to 30. Yeah? So I find it easier to write it down like this. 5, fortunately I have to write it all again. I would write it like this, and then I would write the other one here. That's not official notation, that's just what I find easier to think about. And then the result of the multiplication is here. And so the 5 times 7 is 35. And the 5 times 6 is 30. And 5 times 8 is 40. 5 times 1 is 5. And 3 times 7 is 21. 3 times 1 is 3, and so forth. Yeah? So then it's a bit easier to read what is multiply what. This is 1 times 8, so there comes 8. Okay? So the outer product is a column vector times a row vector, and it leads, and they again have to have, they do not have to have the same length. In this case, they can have different lengths. And the result is a large matrix where the number of rows is identical to the number of elements in the first vector, and the number of columns is identical to the number of elements in the second vector. And the cells are the multiplications of each of these elements. And so implicitly, I have now actually introduced a new concept. Whereas these are vectors, yeah, and the result in the previous of the inner product was a scalar, the result of the outer product of multiplying two vectors, the outer product of two vectors, is a matrix. And so this is what we call a matrix. So a matrix is very similar to a vector in that we have a set of numbers and fixed positions. So this is the first row, first column position, and that makes a difference. You can't just shuffle these numbers and have the same matrix. But there are multiple rows and multiple columns. And so this is what we call a matrix. Just to be sure, any vector is also a matrix. It's just a matrix with only one column or only one row. So everything that applies to matrices applies to vectors, because vectors are matrices. They are just matrices with a specific feature that there's only one row or one column. So here are some more examples of matrices. The matrix M, which is a 3 by 3 matrix with these numbers. And there's the matrix I, which is a 4 by 4 matrix with numbers that are displayed here. The last one is actually a special matrix that we will see quite often. So a diagonal matrix is a matrix with numbers on the diagonal, but not off the diagonal. So a diagonal matrix always has zeros here and zeros here, always. It only has numbers on what we call the diagonal. And this is never, so the diagonal does not go somewhere here. That is not, the yellow thing is not the diagonal. The diagonal is from the top left to the bottom right. So a diagonal matrix only has numbers on this diagonal and has zeros otherwise. And then there's one special diagonal matrix, the diagonal matrix where on the diagonal there are only the number 1. So there are 1s on the diagonal and zeros off the diagonal. This is called the identity matrix, and we will encounter it quite a lot. And it has the feature that it's a bit like the number 1 in numbers. If you multiply any number with the number 1, you just obtain the same number, right? If I do 1 times x, then what I result is x. Yeah? And it's a bit the same with matrices here. If I have a matrix that's an identity matrix, and I multiply it, say, with a matrix X, this also has to be a matrix then, then the result will be another matrix X. Yeah? So if you multiply a matrix with the identity matrix, you obtain the original matrix. So the identity matrix is a very special matrix. It's a bit like the number 1 in numbers, in the sense that multiplying something with that matrix always leads to the original matrix you had. And both of those matrices also have the special feature that they are square matrices. Square matrices means that the number of rows and the number of columns is the same. So here the matrices are 3 by 3 and 4 by 4, but a matrix certainly doesn't have to have this feature. Yeah? So we can have a matrix of any number of rows and any number of columns. If you want to calculate the transpose, the operation is very similar to that of a vector. Every column becomes a row in the transpose matrix. So the first column in the original matrix becomes the first row in the transposed matrix. And the second column in the original matrix becomes the second row in the transposed matrix. And vice versa for rows. So we're just swapping what is a row and what is a column. And again, if you take the transpose of a transpose, you are back at the original matrix, just like we said with vectors. One thing that is important to remember, otherwise you get very confused throughout the text, when we use subscripts, like we did with the V vector, we had V1, V2, V3, and so forth. When we talk about matrices, we always do rows first, columns second, never the other way around. Yeah, so x11 is the first row, first column, x12 is the first row, second column, x23 is the second row, third column, and so forth. And also when we denote the size, we usually use this symbol x. So we say x 4 times 3 means that we have 4 rows and 3 columns. So this is not a square matrix. Yeah? And in practice, we are often going to use symbols. Yeah? So if I write x n by k, it means that this is a matrix with n rows and k columns. If I write y n times 1, I know that we have a column vector with n elements and 1 column. Yeah? And these are not entirely random examples. In regression, we often talk about these matrices. Yeah? So n is normally the number of observations in our regression. K is often the number of variables. So all the independent variables together will be an x n by k matrix. And the dependent variable in our regression will be a column vector of n elements. So don't worry about these now, but this is actually the notation we use a lot throughout the course. Main thing to remember, this is really, really key. When you talk in subscripts about a particular position in a matrix or about the size of the matrix, it is always rows first, columns second. Addition of matrices is similar to addition of vectors. The matrices have to be the exact same size. They need to have the same number of rows and the same number of columns. And then the sum is simply each element added together. So the 4 plus 7 is 11. Yeah, let me point that out. That might go too fast. 4 plus 7 is 11. Yeah. 2 and a third plus 1 is 3 and a third. Yeah. 3 plus 0 is 3. Yeah, so the elements stay in the same place. And we can sum each element. And here's another one of those rules. So we get a few of those algebraic rules that are very helpful to simplify equations later. So just like we learned that the transpose of the transpose is the original matrix, we can also learn this. If we take the sum of two matrices and then the transpose, it is the same as taking the transpose first and then sum them. Yeah, so you can imagine yourself whether we take this sum and then take the transpose of this last matrix, or we transpose this and then transpose this and we add it up together, you end up with the same matrix. You can try this for yourself on paper. So the transpose of the sum is the same as the sum of the transpose. And that is another helpful rule to remember when dealing with matrices. Just like with vectors, we could multiply vectors with a scalar, and we said that we then just multiply each element with the scalar, and we get a vector of the same size. The same is true for matrices. If I have a 3 by 4 matrix, and I multiply that with a number, then I get another 3 by 4 matrix, and each element is that original element multiplied by 4. So 4 times 4 is 16. 2 1/3 multiplied by 4 is 7 1/3, and so forth. Is that true at all? That is wrong. Huh? That is a typo. So 4 times 1 1/3 is 9 1/3. My apologies. Yeah, so 4 times 4 is 16, and so forth. Yeah, that was a calculation error in my slides. The most extensive to explain is matrix multiplication, and so with this we will practice a few times in class. And in this video, I am not going to discuss it in much detail and do it in more detail in the class session. So we can multiply two matrices together as long as the number of columns in the first matrix is identical to the number of rows in the second matrix. So in this example, we multiply A times B, and A has 2 columns and B has 2 rows, and that means we can multiply them. And a bit like with the vectors, I find it myself easier to write it like this, but this is not official math location. This is just how I find it easy. So I put one here, and I put the other one here. And then I think of the products. I'll put a different color to make it easy. The product then ends up here. And you can think of these as vector products. So we already know the inner product of two vectors, right? That was the sum of each of the elements multiplied. So this is the first row vector of the first matrix. This is the first column vector of the second matrix. And this is the inner product of those two. Yeah? So 6 times 3 plus 4 times 4 equals 34. Yeah? So this is the inner vector product of the first column vector, first row vector of the first matrix and the first column vector of the second matrix. Yeah? Similarly, if we have the second row vector here multiplied with the third column vector here, we end up in this number here, and that is 1 times 3 plus 3 times 1 equals 6. Yeah? So we end up with a new matrix that has the same number of columns as the second matrix and the same number of rows as the first matrix, and where each cell is the inner product of two vectors, a row vector from the first matrix and a column vector of the second matrix. And that is why they need to match. Yeah? So we can only calculate this inner product of two vectors if the vectors are equally long. So the number of columns in the first matrix has to match the number of rows in the second matrix. So it is helpful to think of these matrices and so think carefully about the inner product of a vector that we saw before. Look at that carefully, and when you fully grasp that, then the product of the matrices becomes also easier to understand, because you get a matrix. This is basically a matrix of all inner products of all these row vectors with all these column vectors. Yeah, because there are two row vectors here and 3 column vectors here, you end up with 2 times 3 is 6 inner products, and that's all the cells that are in here. Now, the thing that is important to keep in mind, again, to have this set of rules, just like we learned that the transpose of a sum is the same as the sum of the transpose. So we also have a number of rules related to matrices that we multiply. So for example, the transpose of a product of matrices is the same as the product of the transpose, but in reverse order. So notice the order change here, and it's very important. So for A times B times C transposed is the same as C transpose times B transpose times A transpose. Yeah, and so here you can already see that A times B is really not the same as B times A. Unlike with regular numbers, we know that 5 times 3 is the same as 3 times 5. But in matrices, that does not work. In fact, B has 3 columns and A has only 2 rows, so you cannot calculate B times A. that is a matrix that does not, a multiplication that does not exist. Yeah, because the number of rows and the number of rows in the second matrix has to match the number of columns in the first matrix. So A times B we can calculate, B times A does not exist here. But if you take transposes, this becomes a 2 by 2 and this becomes a 3 by 2 matrix, and then it's the other way around. So the transpose of a product is the same as the product of the transpose in reverse order. Another thing that is helpful to remember is that we can play around with these parentheses. Yeah, so A times B times C is the same as A times B times C. Yeah, so it doesn't matter in which order we calculate. So we can calculate this product first and then multiply with A, or we can calculate this product first and then multiply with C. So as we saw here, we cannot change the order. Yeah, so A times B does not mean we can also do B times A, but we can change which multiplication we do first if we have a whole chain of multiplications, which we often do. If there is a multiplication with a sum, then we can separately multiply with the first and then sum and multiply with the second. Yeah, so that operation we can do, and that works with both pre-multiplication and post-multiplication. Yeah. So either way we can separate this out. All these operations you're going to see already applied in the second lecture. Yeah? So these are not just abstract notions that never really appear. They will appear in this course and quite soon. A few special matrices I want to highlight. A symmetric matrix is a matrix that if we take the transpose, we get the exact same matrix again. Yeah, so most diagonal matrices are, every diagonal matrix is by definition, so I have a 2 and a 3 and a 0 and a 0. This is a diagonal matrix because only on the diagonal are there numbers. And if I take the transpose, I end up with exactly the same, right? So the first column in the first one becomes the first row here, and the second column becomes the second row here, but I have exactly the same matrix. So this matrix is symmetric. But also if this had been a 3 and this had been a 3, then the result also would be the same. It's not a diagonal matrix anymore, but it's still a symmetric matrix. Yeah. So a symmetric matrix is one way. If you take the transpose, you get the original matrix back. An idempotent matrix is a matrix where if you multiply it with itself, so A times A equals A. If a matrix is idempotent, then this is true. Yeah, so that's the definition of an idempotent matrix. So they are relatively straightforward. The next two are a little bit more complicated, and you would have to think a bit longer about what that means. And it's hard to get your head around, but it does appear a lot in econometrics, which is the positive definite and the positive semi-definite matrix. And I just want you to take this as a given and just sort of memorize it. So if we have a vector x that is not just zeros, but it has numbers, because if you multiply something with 0, then you get 0, then it doesn't really matter what is in that number originally. But so if you have a set of numbers in x that is not 0, and you take it as a row vector, multiply it with a matrix, and then multiply it with a column vector, then you get a single number. Yeah. So this results in a single number, and that number is going to be always positive. Yeah, you can see if we multiply a matrix with 3 columns by 4 rows, right, with another matrix. So this is A times B. And this one has 3 rows and 4 columns, and this one has 4 rows and 1 column. Then the result is going to be a matrix that has 3 rows and 1 column. Yeah, because these always have to match for the multiplication to work, and the result is always this by this. Yeah. So if we take a matrix that looks like this, x prime a and times x, then this x prime is a matrix that is 1 by by some number, yeah, by 5, say, or by n. This has to be a square matrix, otherwise this whole operation doesn't work. So this is n by n. And this is a column vector, n by 1. Yeah. So this multiplication only works because they are the same. This multiplication only works because they are the same. And so the result will be 1 by 1. Yeah. So it will result in a 1 by 1 matrix. And a 1 by 1 matrix is just a scalar, it's just a number. Yeah. So this is a scalar. Yeah. So if we have a square matrix, so positive definite matrix is always square, otherwise, because this n is the same n as this n, so it couldn't work otherwise. If a square matrix is positive definite, if when we pre-multiply it with a row vector, with a transpose of a vector, and we post-multiply it with that vector, whatever this vector x is, we don't need to know what x is, just any, then the result is going to be always positive. Then we have a positive definite matrix. And semi-definite if it's always either positive or 0. Yeah? This x prime x is a sum of squares. So you remember that from earlier slides. So x prime x is a sum of squares. So x is not, squares are always positive, right? So this is not going to generate any negative numbers. This x prime x part is always positive. So it will only be negative if there are negative numbers in A. But a positive definite matrix can definitely have also negative numbers in it, where in a way that still the result is always going to be positive, positive semi-definite. So a positive definite matrix does not mean that all the elements are positive, but it does mean that if we have it in a sum of squares like this, integrated, then we need to get numbers that are always above 0. One element of matrices that I still want to discuss is the matrix rank. The rank of a matrix is the number of independent columns or rows in the matrix. So we should not be able to come up with some vector, a vector that is not zeros, where if we multiply x with that vector, we end up with just zeros. In other words, so columns should not be able to vector, to be linearly related to each other. And there's a few rules around ranks that are helpful to know, that the rank of a matrix is the same as the rank of its transpose. It's also the same as the rank of its multiplication with itself transposed in either post or pre-multiplication. And the rank of a product is the lowest of either the rank of the first matrix or the rank of the second matrix. So whichever is lowest, that will be the rank of the product. But rank is really a bit hard to understand without example. Yeah. So in this is a matrix where the 3 are really independent. The rank is 3 and there are 3 columns. Yeah. You cannot come up with a column V that results in a product being 0. Yeah. So there is no V that you can post multiply A with where the result is a vector a vector of zeros. Of course, if you multiply with 0, then yes, but that's not the point. Now here's one where there is a linear combination. Yeah, and the linear combination is that these first and third column are related to each other. This column is 3, 2, and 1, and this column is just 3 times that. Is 3 times 3 is 9, 3 times 2 is 6, 3 times 1 is 3. And that means that if I multiply with a matrix with a vector that is 1, 0, and minus a third. So in other words, this is saying take the first matrix one time and then divide the third matrix by 3 and subtract it. Then I end up with 3 minus 3 is 0, 2 minus 2 is 0. Yeah, so I end up with a matrix that looks like this. And that means I have all zeros. So the rank of this matrix is not 3. Because this one is perfectly linear dependent on this. Yeah. If I know the value in the first column, I can exactly predict the value in the third column. They are not independent of each other. They are linearly perfectly correlated. And that means that I can come up with some matrix that does not consist of just zeros. And if I multiply with that, then I'm going to end up with a result that is all zeros. And that means matrix B has a rank of two independent columns. And so the rank is 2. And we call this not being of full rank. So when we talk of full rank, we can say matrix A is of full rank. Every column is independent. So the number of columns is identical to the number of to the rank. B is not of full rank because there is this linear dependency. And so here there's a clear linear dependency between 2 columns. Here it's a bit more complicated. It's between 3. So the third one is really 3 times the first plus half times the second. Yeah, 3 times 9 plus half times 5 is 11.5. 3 times 2 plus half times 2 is 7. And 3 times 1 plus half times 4 is 5. So if we multiply this with the 3, half, and minus 1, we end up with a vector zeros. Yeah. So again, the rank here, this is not a full rank. This is a rank of 2. So we will not actually deal too much with ranks. You don't have to worry about it too much. If a matrix is not of full rank, it is going to lead to complications when you use it in modeling. So you can, for example, imagine a regression analysis where 2 variables are perfectly correlated with each other. Yeah, if I have I just make a mistake. So I have one variable that is constant and I also have an intercept. Then these are perfectly correlated with each other. We end up with a matrix that does not have full rank. And then we do get problems. But this is pretty rare. And we will talk about it later. So it's not a matrix algorithm. You don't have to come up with this vectors V, and you don't have to worry about too much about matrix rank. Generally, we have full rank. But we are often making the assumption that we have full rank, and you should know what that means. What is really important, but what I'm not going to discuss here, is the inverse of the matrix. The only thing you need to know for the purpose of this course is the definition of the inverse matrix and 2 of the rules with it. So the definition of an inverse of a matrix is if I either pre-multiply a matrix with its inverse or I post-multiply a matrix with its inverse. Either way, I get the identity matrix. Yeah. Think of the number 5 multiplied by the inverse 1/5, yeah, I end up with the number 1. Yeah. So if you multiply 5 with 1/5, you get 1. Or if you do 1/5 times 5, you get 1. So there is something special about the relationship between those 2 numbers, yeah, in that they always result in 1 when you multiply. And it's the same with matrices. So this we could also have written actually, yeah, in normal algebra. You could write this as 5 times 5 to the power minus 1 equals 1. Yeah. So when we multiply 5 with its inverse, we get 1. And the same is true for matrices. So when you have the inverse of a matrix multiplied with itself, or a matrix multiplied with the inverse, you end up with the identity matrix. Remember, that was the diagonal matrix with all 1s on the diagonal and zeros everywhere else. And I told you that's a special matrix. It's a special matrix because of this. Now, how to calculate this one? So this only works with square matrices. So it only works if A is a square matrix. And this A inverse is the same size as the original matrix. So if this is a 10 by 10 matrix, this is going to be a 10 by 10 matrix. But how exactly to calculate the numbers in this matrix, that I really leave is not for this course. Yeah? So that is, if you do a matrix, an algebra course, you will definitely get taught that. It's important and there are computer algorithms for it. We are not going to worry about it. We just want to know this definition. If we pre-multiply or post-multiply a matrix with its inverse, we get the identity matrix. And then there's 2 rules that are helpful to remember. One is that if we take the transpose of an inverse, it's the same as the inverse of the transpose. So it doesn't matter which operation we do first. And if we take the inverse of a product, it's the same as the product of the inverses, but in reverse order. Yeah. So those 2 rules we will occasionally see in the course when we simplify equations. One more thing that I want to explain about matrices is called the trace. The trace is the sum of the diagonal vectors. So as we said, the diagonal always is from top left to bottom right. So it's these numbers, that is the diagonal. And the trace is simply the sum of the diagonal. This will be our code to say that, which is 4 plus 8 plus 3 plus 1. Yeah? Or another way to write this for a matrix is the trace would be of a cell, the 8th element, II. Yeah? So we said that the first number is the row and the second the column. So if I do both, so the observation A11 and A22 and A23 and A44, they are all on the diagonal. So this is another way of writing the trace. Yeah? So the trace is the sum of the diagonal elements.